present lecture regards water cycle and waste management. The first point is water supply. Water is essential for the environment, food security, and sustainable development. Fortunately, we have different sources of water: rainwater, rivers, lakes, and groundwater. Because of rapid population growth, combined with industrialization, urbanization, intensification of agriculture and water-intensive lifestyles, a global water crisis has developed, exacerbated by climate change. Access to safe water and sanitation remains a problem in many regions of the world. In fact, about 660 million people do not access drinkable water in the world. Water availability is also affected by water loss, that is, water lost through leakage in distribution networks. In many cases, water loss is more than the half. To reduce this problem, effective strategies and applied technologies to control leakage are needed. Other strategies for improving water availability are to reduce the amount of potable water used for not potable application and to reuse treated water. In relation to water conservation, design and management of communities and buildings have a pivotal role. For example, design can support to install efficient equipment in buildings, especially for toilets, and to develop systems to harvest rainwater, as shown in these figures. In addition, clean water supply could be improved by norms for water quality from various sources and related standards for different applications, and to regular check of the overall supply system. Let us consider the other side of the cycle, wastewater. Wastewater treatments are the basis for preventing water-related diseases, for preserving lands and water safety, and for reusing water. Wastewater collection and treatments are not available in many regions of the world. Globally, we have 700 to 900 million of cubic meters wastewater per day in the world, and the most part is not treated. However, many treatment systems are available depending on the scale and on the local conditions. For treating water, we can have big plants for large communities or small systems such as composting toilets, septic tanks, EMOF tanks, and other off-site treatment systems. The picture represents a scheme of a conventional plant where wastewater is treated, producing clean water and sludge as output. Many physical, biological, and chemical stages take part in the depuration process. Sludge are separated and collected and then treated by anaerobic or aerobic digestion. Biogas production is possible by different technologies at different scales. Biogas production represents an effective example of how water cycle and energy are connected. Biogas can be also upgraded for producing biomethane, depending on the context. Let us focus the input and the output of the process. The picture represents a scheme explaining how water supply and wastewater treatments are connected, referring to the water use in buildings. It means that water cycle has to be faced holistically, considering all the available and accessible technology in an integrated approach. Let's move now to the second topic of the lecture, waste, which is one of the most important flows of metabolism in communities. Urban waste represents a sanitary problem firstly, but it can become a source of energy and matter. There are still many cases in which municipal solid waste is usually dumped in landfill sites or open dump sites, leading to air and water pollution. Conversely, sanitary landfills need to be carefully designed and people need to be trained in management and maintaining them. To face the problem, it is important to collect and analyze data. They regard mainly waste generation per capita, waste composition, and main practice for waste management. These data can be highly variable as they depend on many factors. For example, in the developing world, composition consists mostly of organic material from food consumptions, ashes from fuel wood and charcoal. The composition, in particular the quantity of organic matter, affects the content of humidity and the heating value of waste. These parameters affect the suitable technologies for waste management. Further, other site-specific factors should also be taken into consideration, such as accessibility to waste collection points, cost of storage and transportation, willingness to segregate waste to assist recycling, willingness to pay for waste management services, and opposition to sites selected for waste treatment and disposal facilities. The application of the 3R approach, the same adopted towards a zero-waste paradigm, could be very useful in waste management, also for facing it as a sanitary problem. 3Rs means reduce, reuse, and recycle. Where feasible, the integrated waste management approach should include waste separation and collection, recovery of materials, energy recovery, and final disposal. The solution has to be not merely technical but also organizational. All these components are a part of an whole. In conclusion, availability of drinking water and provision of sanitation facilities are the basic minimum requirements for healthy living, and designers should take into account all these issues.